An application of the derivative in Calc 1 is to take a given function and perhaps an interval of input values and find the largest and smallest value of the function. Now, the way that we would do a thing like this in Calc 1 is take a derivative, 3x squared minus 3, set that equal to 0. I'll skip the algebra, but then you'll get x equals plus or minus 1. Those two values of x are critical numbers, and then we should just see what y values we get. So go ahead and take x equals 1, take equals negative 1, and run them through the function f, and you get y values of negative 2 and positive 2. But that's not all. We should see what happens when we look right on the boundary. So what happens if we're only trying to consider x values between negative 1.5 and positive 3, because that interval was just provided in the question, we should check the boundary. So we'll compute f of negative 3 over 2, that happens to be 1.125, and then we'll compute f of 3, happens to be 18. Clearly, I used a calculator here just to try to not belabor the point. Let's just take a look at what the graph here looks like and then make some comments. So you'll notice if we look at the portion of the function that we want, right? So this is really just from x is negative 1.5 all the way up to x is positive 3. Then we had computed x equals negative 1 and x equals positive 1 as critical values. So those are places where we knew that the slope of the tangent line was 0, right? And those are potential places to look for a local max or local min. But if we really just wanted the biggest possible value, biggest possible y value, just looking where the function kind of levels off, where the slope is 0, isn't going to be enough, because right where that cutoff kind of abruptly occurred when x equals 3, that just happens to be the place with the largest y value, just because a cut occurred instead of where the function, kind of peaked, right? So we checked that boundary point. There's this other boundary point. This boundary was neither the min or the max in the global sense. So we have a local max when x equals negative 1. We had a local min when x equals positive 1. It also happened to be the global min. So among all the points we're looking at, the actual literally smallest y value, the largest possible y value was 18. 0.3 comma 18 here. That happened to be the global max, and it occurred at a boundary. So going back, f has a global max at x equals 3, and f had a global min at x equals 1. The global max in this case was can be found at a boundary, just generally speaking, like in this example, that happened at the point 3 comma 18. Now in this example, f had a local max at x equals 1. Recall that if the first derivative is 0, or doesn't exist, so that's what a critical number is. Typically, it's because the first derivative equals 0 instead of the first derivative not existing. That can occur, but it's kind of rarer. So let's think about the first derivative is 0, so the slope of the tangent line is 0. And then if the second derivative at that same x value is negative, then f has a local max at that x value. How does this negative correspond to local max? Think about it. The second derivative being negative means that you have a concave down graph. So if f is concave down, that shape is going to build a hill, right? So you see actually here, right, concave down, along with the slope being 0 right at that point, that created a local max. Okay. Yeah, I didn't realize it. I have it here. Second derivative negative means the shape is concave down, right? That's why you have a local max. Um, this may have been called the second derivative test in your Calculus 1 book, depending on what book you used. We'll see in Calc 3, there's sort of a version of the second derivative being negative leads to a local max. We're going to see that in just a moment. So let's just do a second review problem of optimization from Calc 1, because it's going to illustrate an important idea. Find all local mins and maxes of a new function, g of x equals x cubed. So we take derivative, set equal to 0. When we set 3x squared equal to 0, the only solution we get is x equal to 0. Right? That's the only critical value then. And then is there local min or local max? Well, let's compute the second derivative. So starting from g prime of x is 3x squared, we'll compute a derivative from that. So g double prime of x is equal to 6x. And then when you plug in x equals 0, so g double prime of 0 is 6 times 0, in other words, 0. Well, that means we don't have concave up or concave down, right? It's sort of flat concavity here, right? So had we had g double prime of 0 being bigger than 0, there would have been a local min, right? Had we had g double prime of 0 is less than 0, there would have been a local max. But because we had neither occurring, g has neither a local min nor a local max at x equals 0. Right? This is what the picture looks like. In fact, we know that there's an inflection here. And we're going to see something similar to an inflection point in our Calc 3 version of optimization.